All right, welcome back, everybody. Today we're going to continue getting into the nuts and bolts of solving these differential equations numerically. In particular, we're going to take a look at those implicit methods. So, for example, we discussed how. Let me get the stroke thickness right here. There we go. So we discussed last time, or not even necessarily last time, but when we first introduced implicit methods, how implicit methods often lead to differential or algebraic equations that are difficult to solve. And you can always rearrange this equation into something like f of x is equal to 0, right? Just move everything over onto one side of the equation. All right. So one of the preferred methods for solving these algebraic equations is via iterative methods, where you essentially guess, check, improve, and repeat. Right. So often these sorts of algebraic equations can't be solved analytically and hard-coded in. They have a form that's more complicated than that. Maybe they might be transcendental or something like that, right? Like an equation that has sine of x and e to the x in the same equation, you can't necessarily find a clean algebraic expression for x. Okay, so so to solve, we use iterative methods. Which can consist of a guess, a check, an improvement on your guess, and then you repeat it. Okay, and you do this many, many times until you hit some sort of user-defined convergence criteria. Okay, now there are two types of iterative methods. Okay, the first one is a bracketing method. So this is where you choose two random points as guesses. You hope that they contain the or a root of f of x equals 0. Hope they contain a root of f of x equals 0. And then you move the points inward, right? Inward. Okay. Two different methods for doing this are methods called Regula Falsi. We'll actually cover that one today. And the bisection method, which essentially is what it sounds like. You just keep bisecting the interval to see if the point is now in the left or right hand subinterval. And then, so the issue with these is that they're slow. So these methods are slow and not commonly used. Right. There's the other type of method, broad category method, is an open method. So, as the name suggests, you choose two random points, but they don't have to bracket the root. So choose two random points, but they do not have to bracket the root. Or said more simply, the root does not have to be in between the 2 points you chose. Okay, so here are the most popular methods or open methods are Newton-Raphson. Oops, I think I got that backwards there. Let me double check. I want to make sure I spell this correctly. Yeah, it is that. It's Raphson. Okay, and then there's also the Secant method. These are both the most popular. Right, and then also we before touched on when we did our first iterative solution method, and we were talking about implicit methods, we introduced the fixed point method, and fixed point is one of these as well. But like we alluded to before, it's not the best method. Okay, so sometimes these do not converge. And if that happens, then you move to a bracketing method. Which, of course, always converges. Okay, so that sort of sets the lay of the landscape. The first thing that we want to do before we start jumping into these new methods is I want to revisit the fixed point iteration. Okay, so this is where, remember, you have to rearrange the equation such you have x is equal to g of x, right? And let's look at an example, right? So consider f of x is equal to x minus e to the x over 4. Okay, so we would like to find the roots of this function. That is, we want to solve x minus e to the x over 4 is equal to 0, right? And again, this is not simple because we have an e to the x and an x involved. If we want to undo the exponential with a natural log, then we have to envelop the x in a natural log, which is not solving for it, right? So what does this look like, first of all? Draw right here. It's where the y-axis is f, the x-axis is x, and in actuality, the roots are here and here. This root is 1.43. This root is 8.61. And then you have kind of this overall shape. And that's a little bit steeper on this side. Okay. Now, in order to use fixed point iteration, we rearrange to x equals e to the x over 4, right? And now we're looking for the points where the lines y equals x and y equals e to the x over 4 intersect, right? So what does this look like now? So we have this, I'm just going to call the axes x and y. So the first plot, and let's just call it the x, is just going to look like this, just a linear. So this is y equals x. And then we'll also put the exponential in there as well. where you have something like this, of course, off in that direction, and that's y equals e to the x over 4, right? And of course, the two intersections are going to be the same as before. Oops, sorry. So that same one at 8.614, or sorry, 61, so 8.61, and then this first one over here at 1.43. Okay? And so how does this work, right? Well, let's assume that we choose a initial guess of x naught equals 7 or something. So like x naught equal is 7, we'll say right here. X naught, right? So let's recall how fixed point iteration works, right? So the idea is that you take your guess, you plug it into the function. In this case, it would be e to the x over 4, and then you see what you get, and then that's your next guess. So in other words, I'm going like this, okay, and I'm seeing what the value is. That's the value on the red graph. I'm going to trace the horizontal line over to here, okay, and that's the y equals x line. So that's going to give me my next guess. So I'm going to go down here, and this is x1 now, right? And now I'm going to figure out what the value is for that one. And I'm going to go over here, trace it over horizontal. And it's going to be that value, which is going to be down here, and that's going to be x2. And this is going to go over here, and that's going to be x3, and so on. You can see how we're going to converge down to the 1.43 root, right? Okay, so we're going in this direction, denoted by these arrows. Okay, hopefully that makes sense. If you started over here, for example, you're also going to converge. Like if I have a guess over here, it's going to go this way, and I need to trace that over to this, which should be here, and then I'm going to go here, and then the next evaluation is going to be there, and go in that direction. So in other words, we're always going to converge on this 1.43, but let's look at what happens over here. If we selected a initial guess that was larger than 8.61, you're going to get a value that's bigger, and you're going to get carried off in this direction, up and away, sort of over in this direction, and you're never going to recover the 8.61 root. So the 8.61 root cannot be found with fixed point iteration, or FPI. Okay. So like, one thing that we had derived before was that, or I should say recall that we had this sufficient but not necessary condition that g prime of x had to be less than 1, right? So sufficient but not necessary. For instance, if we look for this case, right, g prime of x is equivalent to 1/4 e to the x over 4. If we set that equal to 1, then x is equal to 4 natural log of 4, which is approximately equal to 5.545. So, in other words, our initial guess, our x naught equals 7, has a larger g prime of x in magnitude, but still converged. Right, so this method is a little messy. Where there's going to be roots that you can never reach, and there's also a you can see that there's not a very clear way of knowing whether or not an initial guess is going to converge. Right. So, but here's another interesting point, right? So let's look at another case. So there's nothing that said that we had to rearrange the equation in exactly that way, right? So we could have done, consider the following rearrangement. Where we have x equal e to the x over 4, but instead we write the natural log of x is equal to x over 4, which is, of course, simplifies to, in fixed point iteration form, x is equal to 4 times the natural log of x. Okay, well, what does this look like, right? Well, now we're in this situation where we still have the linear y equals x line, but now we have a logarithm coming up and across like this, right? So that's the 4 natural log of x line. And if you look at what happens when we make an initial guess, say here, if we follow that up to the red line and then carry that over to the next guess, so that's going to be x1 and here and so on, and kind of bounce up and down, you can see that in this case, we're actually converging. So now we converge to 8.61, right? So depending on how you rearrange the equation, you're going to converge on different routes. So, we already had said this, but the bottom line is FPI is not a good approach. Okay, so with that background, let's go ahead and take a look at Newton-Raphson. So this was published in 1690 by Raphson. Of course, it bears Newton's name because he had sort of independently discovered it, or used a similar method first, right? In 1671 is when Newton had used a similar method, but of course Raphson, who lived from about 1668 to 1712, published his result in 1690. And you can see this is actually an interesting little letter here. So this is when Raphson was elected a fellow of the Royal Society. And you can see that the recommendation, or his conference or induction into this society was signed by Edmund Halley of Halley's Comet fame, and Halley actually also was the one who recommended him to be part of the Royal Society. But really not much else is known about Raphson's life. So, but definitely in the mix of that really sort of illustrious time in English history where they had some really great, Enlightenment thinkers, let's say. Okay, so going back in Newton-Raphson, we're going back to solving f of x equals 0. Okay, so as with anything else in this, or seemingly everything else in this class, this method is based on Taylor series. On Taylor series. Okay, so what we're going to do is consider the Taylor series expansion of f of x centered at the current guess which we'll denote as x raised to the k in parentheses. And so in general, when you have an index in parentheses, that you're denoting a guess. I may have mentioned that before. Okay, so that's the center, and then we're going to evaluate it at the next guess. Which is x to the k plus 1. Okay, so what does this look like? Well, it's f of x to the k plus 1 is equal to f of x to the k, okay, that's the first term of the Taylor series, like evaluated at the center, plus x to the k plus 1 minus x to the k, multiplied by f prime of x to the k, plus x to the k plus 1 minus x to the k squared divided by 2 factorial multiplied by f double prime evaluated at x to the k, and so on, okay, higher order terms. So what we're going to do is we're going to truncate second order and higher, and then assume x k plus 1 is the solution, okay? Okay, and what do I mean by that? What I mean is that we're assuming that f of x k plus 1 is exactly equal to 0. Okay, so we're assuming that our next guess is we're gonna guess it right on. And when we do that, if we make that assumption, we get the following relationship where 0, which is what the left-hand side of the equation, right, is approximately equal. The approximately equal is there because we truncated. Okay, it's approximately equal to f of x to the k plus x to the k plus 1 minus x to the k times f prime of x to the k. Okay, so I'm going to label this with a star because we'll use it in just a moment. But then we get this update rule, which is x to the k plus 1. So we're just going to solve for x to the k plus 1 in that equation above. X to the k plus 1 is equal to x to the k minus f of x to the k divided by f prime of x to the k. Okay, so this is our update rule. So of course, now it seems like almost like a bit of sleight of hand. It's like, okay, we're just going to go ahead and assume that x to the k plus 1 is the solution, and that's totally fine. The reason why we don't actually get the solution in a single jump is because this update rule is based on a truncated Taylor series. So the right-hand side of this expression is approximate, which is why that sort of approximately equal sign is there. Okay, so given that update rule, let's really quickly show how quickly this converges. Let's show how quickly this converges. So now evaluate, instead of at xk plus 1, evaluate it at x bar, which is the true solution. So now evaluate the Taylor series above at x bar, the true solution. So this is another exercise in making an assumption here for mathematical reasons. So instead of f of k plus 1, we have at the top of the screen here, we're going to do f of x bar which is going to go to 0. Okay, and then we have f of x to the k plus x bar minus x to the k times f prime of x to the k plus x bar minus x to the k squared over 2 factorial f double prime of x to the k, and so on. Okay, and the thing is that because the way we defined x bar here, this thing, we can actually just call that epsilon to the epsilon of step k, or in other words, the error of the kth step, right? It's how far off is our guess from the kth step, or sorry, is our guess at the kth step from the true value. Okay, so now subtract our update rule. Which we labeled with star from the above, from both sides. Right, so we have 0 on the left-hand side, so we can leave that in place. And what you end up with is 0 equals x bar minus xk, the kth guess is f prime of xk minus x to the k plus 1, or the k plus 1th guess, minus x to the k times f prime evaluated at xk plus, and I'll just write this as epsilon k squared over 2 factorial times f double prime of xk, and then there's higher order terms there. Okay, now looking at this subtraction here, you can see that this xk times f prime of xk is going to cancel because we have a minus sign in the middle here, so these two guys go away. And what we're left with is we have an x bar minus xk plus 1. So that's the error in the k plus 1th guess, right? And so what we end up with is that epsilon k plus 1 is equal to negative or minus f double prime of xk divided by 2 times f prime of xk. So that's from the what comes from there, and then this is all multiplied by this epsilon k squared, right? So in other words, error of the next step is proportional to the error of the current step squared, right? So we call that second order convergence. So convergence is second order. Okay. So if our error at our current step is very small, then we're going to square that number, and that'll be our next step. The error will be about the same, or will be proportional to that number. Okay. Okay. So a few notes about Newton-Raphson. First off, we need an expression for f prime. Okay, this is not always doable in practice. It could be that your f is non-analytical. There's a number of possible issues there. It may not be differentiable. Might have some problems. Okay, and then also, if f prime of xk, or the kth guess, is approximately equal to 0, then you're going to run into issues. run into issues, and let's sort of see why. Let's look at our update rule here, where let's actually sort of underline this to make the point that's the update rule. We're going to code it up later. If f prime of xk is 0 in this scenario, then your next guess is going to be really far away, right? You're dividing by 0 and you're adjusting by that value. So the next value is you're going to run off in the positive or negative direction really far away. Okay, so that can cause some problems, and I'll show you an example of that when we go through the Jupyter notebook. Now, there's a couple other things that actually can cause this method not to converge. So if f double prime is equal to 0 or close to 0 near the solution, like near the actual root, you can get stuck oscillating around it. Get stuck oscillating around it. So what do I mean by that? Well, let's draw a little scenario here. When f double prime is equal to 0, that's the same as being at an inflection point. So let's say we're looking at f over x here, and we have this function that looks like this. It's kind of increasing, and then it curves upwards, and then goes off like that. Some sort of, what is that, like a hyperbolic tangent function or something? So let's say that your guess is this guy right here, and you follow it up. And the way that this method works is you take the tangent line to where your guess is, and you follow that over until you hit the x-axis, and then you go up and do it again. Well, if you do it over here, then you're going to follow. You might end up going back to this spot, and that spot's going to take you back over here, and you just continually, continue in this loop, and you're always missing the true solution in the center there. Okay, you can also get stuck near local minima. Also get stuck near local minima. So what I mean by that is, let's say we have f like this, an x, and we have like a parabola shape. Well, from this point, you are going to follow a, here, let's draw that a little bit better. So from this point, you're going to follow the tangent line over this side, like that, and you're going to go up here. So you go like this direction, and then you're going to go up to here. You're going to follow the tangent line over to the x-axis there, and you're going to go back up to the same spot and continue the same thing over again. So you're kind of going up and over and up and over, and you're not actually converging to any sort of root. You're just getting stuck near a local minimum. Okay, so that's one of the issues with Newton-Raphson. So, despite those cases, Newton-Raphson is actually very commonly used due to its fast convergence. So, NR converges fast. So, is used often. Okay, so let's go over the secant method, and then we'll go over one bracketing method, the Regula Falsi method. Okay, and then we'll go and see how to implement these things. I would like to do that. Forgot to do that section. Okay, so like I said, let's talk about the secant method. Okay, so the secant method is actually just a common sense extension of Newton-Raphson. Okay, so extension of an R where you approximate f prime using a rise over run approach. Approximate f prime using a rise over run approach. Okay, so you need to use 2 successive guesses. So what you end up with here is the next guess, xk plus 1, is equal to xk, or the kth guess, minus f of xk times this quantity, which is xk minus, xk minus 1, so the last 2 guesses, right, divided by f of xk minus f of xk minus 1. Okay, so what are you looking at here? You're looking at essentially the difference in the function between the last 2 evaluations divided by the last 2 evaluation values, 1 over that value. So it's like the same. If you look at the updated rule for Newton-Raphson, you have f over f prime evaluated at that point. Well, now we have f evaluated over a rise over run approximation of f prime at xk. Okay, so it's like this thing is approximately equal to 1 divided by f prime evaluated at xk, or the kth guess. Okay, so what does this look like graphically compared to Newton-Raphson? So let's say if we have a function that kind of looks like this. Sorry for the messiness. If we choose an x naught here, we follow it up, we pick the point, and then Newton-Raphson drops that tangent line to the x-axis, right? Sorry. Let me make sure that's, there we go. And then this becomes x1, right? So this is Newton-Raphson. For the secant method, it would look like this. So I'll try to draw roughly the same kind of plot here. And we have x naught, and let's say we have an x1. We define an x1 here. Here, let me actually move this line so it's a little bit easier to see. Apologies. I'm going to stretch it out horizontally a little bit so it's a little bit easier to see. So let's see, this is x naught, and then we'll do a second guess of x1, right? And what you do is you grab these 2 points, and you take the line that goes between both of them, right? And then you follow that down to the x-axis, and then that constitutes your next guess, or determines your next guess of x2. Okay, so it's just a line passing between the 2 points that you chose with their function evaluation, and then you follow that down to the x-axis. So you can see how you end up getting a very similar overall convergence behavior than as Newton-Raphson. It is slower, so secant is slower than Newton-Raphson. But it's still much faster than FPI. Still faster and more reliable than fixed point iteration. Okay? All right, and then the final method that we'll go over today is the false position, or Regula Falsi method. Regula Falsi. Okay, so this method actually uses the same update rule as the secant method, but it's a bracketing method, so the point must be between the 2 guesses. So he uses same update rule as secant, but is a bracketing method. Okay, so what does that mean? Like bracketing method, what I mean is that we need that f of x, I'll call it u, which could be like the right hand guess times f of x L, or the lower value, or the left hand guess, has to be less than 0, right? It has to bracket a root. So those two need to be multiplied by each other and result in 0. So the update rule looks like this, where you have x new, your new guess, is equal to xl minus f of xl multiplied by xl minus xu over f of xl minus f of xu. Right. And then you have a decision to make. If f of x new multiplied by f of xu, or upper, is less than 0, that means that your new point is in between your f of x new and f of u, okay? And so then you have to sort of reset or rename xl to x new, right? Else, if f of x new times f of xu is greater than 0, well then you're going to reassign xu to x new. Okay? So converges slowly, just uses a fallback. As a fallback. When above methods do not converge. Okay? So what's going on here? Let's just say that very quickly we have a function that's doing this, and we have an xl and like an xu, and then we put our x new ends up being here x new, right? So all we're doing is we're just checking to see if f of x new is negative in this case, and f of xu is positive. So then you'd have their multiplication. You can multiply the two together. It would be less than 0, and so then you can rename. You make x new your new xl, and then you do it again. Okay, it's just a way of figuring out where the root actually applies, where the root actually exists. Okay, and you can see how over time it's going to shrink your bracket until you get very, very close to the actual value within a user-defined tolerance. Okay, all right. So that is the end of the paper and pencil work for this lecture here. Now what we're going to do is we're going to transition over to the Jupyter notebook and fill in some of these methods, and then I also wrote up some code that tries to illustrate how things actually converge. Okay. All right. So let's go ahead and do our import statements here. And here's the function that we want to work with today. If I plot it, it looks like this. Let's go ahead and do a multiple windows here so it fits nicely. So you can see it actually has two roots, one at about 3, one at about 6, and it has some, fairly interesting variation going on. And so what we would like to do is first we also derive define the derivative so that for later when we want to use Newton's method. But it's just normal analytical derivative, nothing crazy going on there. So let's go ahead and do it. So fixed point iteration, right? So fixed point iteration was the simple method to implement. First, we need to rearrange the function. So I actually just rearranged it for x. So I moved the x cubed over 10 to one side, and then solve for x. And so and I define g of x in that way. So the next guess is just going to be g of x current, right? It's just that simple for fixed point iteration. And then we're going to check our tolerance, basically. So if the absolute difference, oops, I put another if in there. If the absolute difference of x next minus x current is less than our tolerance, then we'll go ahead and break the loop. But otherwise, we just continually set x next to g of x current. We're appending these values now because I want to show the evolution of this and plot it. But in general, you can just continually do this until you get the right solution. Okay, then I'm converting to an array for plotting, and I have a bunch of plotting functions, and then what you end up with are these two plots. So it took us 18 iterations. So this is what the actual, remember, this is the function that we're trying to get to the solution of, and it found the approximate the root of 3.1812. Okay, and then and you can see that it's printing the value of the root is a very small value, which is good. And what we're trying to find where f is equal to 0. And that's basically 0. So this is where you can actually see what's happening. So this is our guess. Remember, we go up to the function value, we cross over to the y equals x line, and that is where we're going to plug in the next function value and so on. And you can see that we move off in this direction here. Let's see, if we did this one, then we might converge to the same one. So let's try a couple other initial guesses just to see what happens. So we do 2 as our initial guess for fixed point iteration. So yeah, so I did 5.8 there. Let's do 2 just to try it. Conversion 15 iterations, and you can see, yeah, I jumped over to the right here and went down over here. But if we do something bigger than 6, so I think everything on the left-hand side here is going to converge on this same point, but if I chose a value like 6.1 even, let's say, like 6.1, something that's just a little bit bigger than the root that we know exists over there, and look at this, it's blowing up. it's taking a while to plot because there's going to be a lot of not a numbers in these arrays. It might not even plot. I'll wait 30 seconds and see what happens here. I'm not even sure. See, so here we got, it's only showing one guess here basically, and it's blown up to 1 million. Essentially the thing blew up. It's completely lost. So and it also tried 2,000 iterations and eventually got to values that were not numbers. Okay, so just an illustration, fixed point iteration, maybe not the best idea. Okay, but you can see an illustration of how it works here and how it's traversing its way through the plot. Okay, so hopefully that's like an additional, really hammered home the idea of fixed point iteration here. Let's take a look at the Newton-Raphson method. Okay, so we're going to take the f evaluated at the current point and then df. Remember, we defined that up here in the first cell here. And then we're going to perform the update rule, right? So first thing we need to do actually is we need to check for small values of the derivative. Because if this thing is, I'm just going to place it at 1e minus 12, okay? If that thing gets really small, then we're going to print an error message that says Newton method derivative too small. Okay. And then we'll go ahead and break the method off at that point. Because remember, if the df value gets too small, then the method's going to run off. So I mean, this would then basically add something of order 1 trillion to our current guess, which is going to send us off far away, obviously, from where we want to be. Okay. And then the update rule, as you may or may not remember, if you look down your notes, x curve minus f underscore val, right? This is what we evaluated up here, divided by df value, okay, the derivative value. And then we're appending these just to keep track. And then we're doing the same sort of absolute value check we did before. We do x of our next guess minus x of our current guess. And we're going to see if that's less than our defined tolerance value. And if it is, then we'll break and we'll move on. Okay, and so this is a bunch of plotting functions that we'll go ahead and do. And here we go. We converged in only 5 iterations. This time we converged on the sort of x equals 6 root. And let me try and choose one that maybe may be a little bit more informative. So let's do, say, I wonder what happened if I chose 0. So let's do 0 as our initial guess. See, like, look at this. So what happened here, it took 32 iterations. So this was our initial guess. And then the tangent sent us over here near where the function had a local maximum, right? And I told you that around local maximum, you can get some extra oscillations for Newton-Raphson. And that's what happened here. We got kind of stuck there for several iterations until eventually we got fired over to the right here. And then we converged very fast on that root. Okay, let's see if we can successfully converge on the root at 3. Maybe I'll feed it a 4 or 2 or something. See, this one did converge on that 2 root, or that 3 root. And yeah, you can see how it works here. So just 2, followed that over to the x, went over here, followed that down here, and then eventually converged after only 6 iterations. Okay, so that's how Newton-Raphson works. And it was kind of nice to show you how that x equals 0 guess ended up sending us over some oscillations here. I wonder if we put in something right. I mean, what is that, like 1.45-ish or something? See if I can sort of send us off in a far away on a first try here. Yeah, so look at this. So this did still converge after 89 iterations, but what happened was I set an initial guess that was right around where this is, the derivative of this is equal to 0. So it wasn't small enough to cause us to trip our little derivative too small test, but it still sent us way out here to where the function values are 10 to the 36, okay? And even with that case, it still managed to find its way back to the correct root. So, this is an interesting illustration because it shows one of the issues with Newton method with those derivatives being small, but it also shows the power of the method that in 89 iterations, less than 100 iterations, it was able to return from 10 to the 36 and give us the right root. So that's kind of an interesting result there too. So there you go. You guys can play with this once you fill out the code. Okay. So let's add the next method that we wanted to look at here. I think it's secant. Let's see. I want to make sure I'm checking correctly here. Yes, it's the secant method. So remember, the secant method is very similar to the Newton method, where you just take you have to make 2 initial guesses, but then you do a numerical approximation of the derivative. So we're going to do f of x vals. And we're going to take the current iteration minus 2. Okay. And then we'll do the same thing here, but the current iteration minus 1. So f of x vals of the current iteration minus 1. Okay, so we had already appended to x vals with these two initial guesses. We're just lifting those two for the first time through, and then as we continually add values, we'll do this. We're going to put another check here, where we're going to make sure that the denominator is not too small in the secant method. Same idea as before, e to the minus 12. Okay, so print secant, oops, make sure printing a string here. Secant denominator too small. And then we'll go ahead and break the loop. So that's just a little bit of a error handling there. And then the next value is going to be the previous value, of course, x vals of n minus 1. But now we subtract f1 times the difference of the previous two values, x vals n minus 1 minus x vals n minus 2 divided by f1 minus f2. Okay, I believe that's correct. And we append that value, and then of course we'll just do the tolerance check to break the loop if the absolute value of x next minus x vals of n minus 1, the previous value, is less than our tolerance, then we'll break the loop. Okay? And then a bunch of different, plotting functions to do the same thing here. Let's see, I accidentally put in f2 here. What I need to put was f0. Just a little typo there. And here you go. So the green guesses, I think, are our initial guesses, right? We have -1 and 1. And it's a little bit harder to see on this plot, but you can see, follow the line that connects the two green lines to here, and that gives us our next guess, right? And then you do a line between this guy. So this must be considered x1. So you can see a line between this guy and this guy go to here, and then this one and this one go here, and so on, until you end up at the correct iteration. I think that these dashed lines connecting these are actually not quite correct. There's something. Oh no, I think they are. No, I think they're working. It's just a little strange. It I couldn't quite tell what was going on here. Oh, there's a very small hidden dashed line that's sending us right towards the root. But you can see that this one took 13 iterations, and of course everything's going to be sensitive to your initial guess. But we're still finding the roots in this case, and our two initial guesses didn't have a root in between them, so it still worked. Okay, so like I said, I encourage you to play with this. Now, the next one we're going to look at is Regula Falsi.
Yeah.
Okay, so the first thing you need to do with Regula Falsi is you need to check that so these are our first two guesses, a equals 4 and b equals -1. So that's going to place us where we're going to be right here and then -1. So we're definitely going to have a root in between there. And so we're going to check if fa times fb is less than 0. Oh, sorry, greater than 0 is when we want to raise an error, right? Raise a value error that says FA and FB must have opposite signs for Regula Falsi to work, right? And then we're setting our max iterations, a tolerance, we're appending A and B. Okay, and then C is the update rule. It's the false position, so to speak, minus FB times B minus A divided by F of B minus F of A. Okay. And then F of C is just going to be F of C. We're going to keep that value. And then if the absolute value of F of C is less than the tolerance, okay, so remember this is this is now checking to see if we actually hit the roots, because f of c, it should be 0. Okay, if we hit the root, and then we update our bracket accordingly based on whether if we didn't hit this tolerance to break the loop and declare victory, then we need to update our bracket, which has f of a times f of c. If that thing is less than 0, that means that the root is in AC. So then we need to set the bottom, or b, to c, and then f of b to f of c. fb to equal fc, right? And then otherwise, we're going to have the root in cb, so therefore a needs to be reassigned to c, and then f of a needs to be reassigned to f of c. And then you just continue to go through. Okay? And we let that proceed. db is not, let's see, where did I accidentally drop a db? Yeah, we want fb here. Okay, and then this one converged after 7 iterations. Okay, so you can see how this method actually works. So what it does is it draws the line between your two guesses, and it sees where those intersect with the x-axis, and then whether it adjusts its the upper or lower value depending on whether or not your right or left, or your root is contained between your new guess and your left guess, or your new guess and your old guess, or in your right guess. Okay, and you guys can play with checking different sort of initial guesses for this guy. Let's see what happens if we choose something like really large for the second one. Right, so we have both roots contained. What's going to happen there? F of 9. Oh, whoops. So wait, no. Oh yes, yeah. So we actually have to choose something that's we have to choose something that's within the bounds of that 3 and 6, because that's the only part of the function where it's positive. We could choose, instead of -1, we could choose something large, but then we would just get the other root. Right? Oh, that looks kind of nice and pretty. Took a lot more iterations though. Okay, very interesting. Well, I'll let you guys fill that out and play with it. But for now, that's the end of this lecture. We're going to in the next lecture, I believe we're going to move to talking about boundary layer problems. And I think that I might have recorded that lecture actually the very first time I taught this class. So you might see sort of an abrupt change in the video style, and then we'll switch back after that lecture. But for now, I want to say thanks for listening. I hope you have a great remainder of your day, and I'll see you in the next lecture.